Advanced Ceramic Nanocomposites, Lection 1, Introduction. Classification of the nanocomposite structures. A nanomaterial has a typical grain size below 100 nanometers, whereas ultrafine grain materials are characterized by grain size below 500 nanometers. The concept of structural ceramic nanocomposites was proposed by Nihara in 1991 and can be seen as the adoption of the nanocomposite approach for the microstructural tailoring of structural ceramic composites. In order to classify the nanocomposite structures, we should firstly consider the different morphologies of the nanoscale reinforcement. The three types of this reinforcement presented on this slide. In fact, nano-reinforcement can be grouped into three broad categories. The first one is 3D nanofillers such as nanoparticles and nanospheres, which are relatively equiaxed and diameter below 100 nanometers. The next one is fibers or tube having diameter less than 100 nanometers. The aspect ratio more than 100. And the last one, plate-like nanofillers, which can be layered materials with typically thickness of the order of 1 nanometer and aspect ratio in the other two directions at least of 25. The surface area volume ratio for the different types of reinforcement is displayed in the same figure. The changes in particle diameter, fibrous material diameter, or layer thickness from micrometer to nanometer changes the surface area volume ratio by 1 or 2 orders of magnitudes. This means that with the drastic increase in interfacial area, the properties of the composite are more and more dominated by the properties of interface and interface. On this slide, demonstrate the scheme of common nanocomposite structures for ceramic materials. It's a few types of nanocomposite structure where combined the micron size grains with nano grains or nanofillers like nanotubes, elongated structure, or plate like nanofillers, or only nanostructure with nanograys and nanofillers like elongated structures. Nanocomposite structures in ceramics often involve a micronic size matrix. Here you can observe it with embedded nanoparticles. These nanodispersions can be situated with the matrix grain and grain boundaries or occupy both positions, as illustrated on the figure A. It's a classic example is found in the pioneering work of Nihara and colleagues who dispersed the nanosilicon carbide particles within micronic aluminum oxides, silicon nitride, or yttrium oxide matrices. On the figure B and C depict other micro nanostructures featuring elongated grains like whiskers, fibers, or rod-like grains, and the picture C with nanopellets, all embedded within the micronic matrix. These structures are of interest due to the in situ toughening effect from the elongated grains and platelets, which contribute to crack bridging and deflection mechanism. A recent development in composite structure, as described in literature, introduced a combination of rounded and elongated nanostructured second-phase materials embedded in a traditional ceramic matrix as depicted on the picture D. The rounded grains of the second phase act to hinder matrix grain growth during sintering, creating a pinning effect aimed at enhancing composite hardness and strength. Meanwhile, the elongated grains chosen for their toughening capabilities, as previously discussed, contribute to crack deflection mechanism. On the figure E showcases a nanocomposite structure composed of approximately equi-exit nanoscale grains of two distinct phases. This immiscible phase presents in similar volume fraction from interconnected structure where each phase impedes the growth of the other, limiting long-order interdiffusion. This concept extends of three or multiphasic systems as illustrated in the figure F. Increasing the number of immiscible phases also increases in the diffusion distance between homologous grains, further refining the composite microstructure. On the figure G, demonstrate a nanocrystalline composite with grains of single phase separated by grains boundaries with different chemical composition, second phase. And finally, on the figures H and I, exhibit nanocrystalline composite featuring elongated grains or plates of one phase embedded within the nanocrystalline matrix of another phase. To fully grasp the behavior of materials across various length scales in diverse nanocomposite structure, a thorough understanding is crucial. This understanding extends to how the nanoscale structure influences bulk properties, which in turn guides the design of nanostructures for fabricated, advanced, and multifunctional composites. Once this knowledge is attained, tailoring the desired composite structure becomes a challenge yet essential step in the fabrication process. Success here hinders or developing innovative concepts at each manufacturing stage, starting from synthesized composite nanopowders to their processing and sintering. Here you can observe some examples of different kinds of developed ceramic composites and nanocomposite structure. This is a single-phase nanocomposite from titanium nitride grains obtained by up-to-date technology of spark plasma sintering. The nanograin ceramic with enhanced but elongated grains, multifunctional, multiphase nanograined ceramics obtained by rate control sintering, and nanoceramics which combine the nanograins of titanium nitride and nano whiskers of silicon nitride. To achieve a comprehensive understanding of nanocomposite structure, one must delve with the behavior of materials across various length scales. This understanding is crucial for leveraging the influence of nanoscale structure on bulk properties, paving the way for designing increasingly sophisticated and multifunctional composites. Once this foundational knowledge is acquired, the next challenge lies in customizing composite materials to meet specific requirements during fabrication. This endeavor demands innovative concept at each stage of manufacturing, spanning from synthesis of composite nanopowders to their processing and sintering. Presently, there exist numerous technologies capable of producing highly pure single-phase nanocrystalline powders. However, the synthesis of nanocomposite powders predominantly relies on traditional mixing and milling methods, highlighting a significant gap in advanced synthesis technology, particularly for bi- or multiphasic systems, especially at industrial scale. As noted earlier, incorporating nanoscale or ultrafine second phases can lead to significant improvement in the mechanical properties of materials, such as hardness, strength, fracture toughness, and creep resistance. However, achieving outstanding mechanical properties of nanocomposite ceramic hinges on a well-designed and executed fabrication process that results in tailored sintered micro-nanostructures. When designing a composite structure, it's essential to consider not only the chemical composition of the matrix at second phase, but also the quantity, distribution, and morphology of reinforcement phase. One critical aspect is attaining a uniform distribution of the second phase within the matrix material. However, this remains a challenge, especially when using nanocrystalline particles due to their exceptionally high specific surface area and thus a natural tendency to agglomerate. Consequently, every manufacturing step in the product of nanocomposite ceramics must be carried out meticulously, starting from production of composite ceramic, from synthesis of composite powders to forming grain bodies and sintering them. While some previous researchers have discussed in our lectures advanced powder technology, we discuss the processing and sintering routes of different ceramic materials. Here we discuss the nanoceramics only. There is a notable lack of discussing the role of synthesis in shaping and microstructure and properties of sintered composite ceramics. In the following, the mainly used synthesis routes for the composite systems, preferably based on high melting point compounds, will be reviewed here in our lectures. First, the traditional mixing and milling method of single-phase ceramic powders to produce composite feedstock. will be discussed. Then the more advanced synthesis method used for directly producing composite powder will be solved. And finally, we summarize all the data to show how we can synthesize the composite powders and from these powders produce some products for industry. To fully utilize the unique properties of bulk nanocrystalline materials, nanometer size powders must undergo densification to form parts with specific properties, geometry, and size. The critical aspect of nanopowder consolidation is achieving a densification rate while minimizing microstructural coarsening and preventing undesirable microstructural transformations such as grain growth during sintering's intermediate and final stages of Ostwald ripening process. While the densification process for conventional powder is well understood, densifying nanopowders presents significantly additional challenges from both theoretical and practical standpoints. Firstly, the substantial surface area of nanoparticles leads to widespread agglomeration, negatively impacting on the densification process. Moreover, there is an ongoing question regarding whatever sintering mechanism scale with grain size and if this mechanism change at the nanoscale level. Several reviews have already been published addressing nanopowder processing and specific issues related to nanosintering, highlighting the complexity and importance of this process for harnessing the potential of nanocrystalline materials. We will discuss a different method of sintering and of nanopowders, nanoceramic powders, and discuss the grain growth process and densification process in our course. The mechanical behavior of nanocrystalline materials have been extensively studied in over 500 publications and several reviews articles. Many of these studies have found that the yield stress, the micro hardness, and for nanocrystalline materials can be significantly higher, typically 2 or 10 times higher than those for coarse grain polycrystalline materials with the same chemical composition. These findings are often explained using empirical relationships such as patch hole relations relationship which describes these enhanced mechanical properties in nanocrystalline materials. The high strength observed in ceramic nanocomposites are not primarily attributed to an increase in toughness, but are likely due to a decrease in processing and contact-induced defect density, combined with the improved crack healing mechanism upon annealing. Transgranular fracture, often accompanied by reinforcement particles situated in grain boundaries, plays a crucial role in indicating the strength enhancement. Furthermore, the enhancement creep resistance observed in the materials is linked to grain boundary pinning mechanism. Investigation are ongoing to understand the mechanism contributing to increase wear resistance as well For example, is provided for aluminum oxide, silicon carbide, nanocomposites system processed by extensive milling of aluminum oxide and silicon carbide raw material. It was proved that during this step the silicon carbide particles act as grinding medium during a treater or ball milling and successfully destroys the aluminum oxide agglomerates, which commonly cause large processing flows. This is illustrated on this graph, in which we can see a continuous decrease of flexural strength by increasing the flow size in aluminum oxide, silicon carbide ceramic. Values show that the flow size should be very small to produce high strength ceramics, meaning that carefully manufacturing during the ceramic processing is needed. A number of theoretical studies on modeling and variation materials properties with the dimension of each structural element shows that decreasing grain size to 100 nanometer or less nanoscale cause in the material demonstrate extreme properties. For example, the hardness. The classical patch hole equation suggests that the strength or hardness of material linearly increase with decreasing of grain size, which was the base for finding extremely hard, strong nanomaterial. However, no substantial progress has been made toward achieving the maximum mechanical characteristic of ceramic solids, bulk ceramics, with decreasing the grain size. Only the hardness of thin film based on refractory compounds can be made comparable with the diamond by decreasing the grain size. In these lectures, in the spotlight is on ceramic composite materials characterized by microscopically homogeneous structure with a particular emphasis on particulate nanocomposite system. To provide a comprehensive overview, this lectures is dedicated to discussing the synthesis methods of nanocomposite ceramics powders, underscoring the pivotal role of this manufacturing step in shaping the micro nanostructural attributes of these composites and their subsequent properties. We will observe the structural characteristics of single-phase nanocrystalline ceramics and some composites, followed by an exploration of nanostructured composites. The concluding lecture is dedicated to practical route from the synthesis methods of nanocomposite ceramic powders, consolidation of nanocomposite, underscoring the pivotal role of this manufacturing step to shaping the micro nanostructural attributes of the composite and their subsequent properties. Thank you for your attention.